Yeah, I have started recording the session. We'll post the recording later on. Can someone just confirm that the screen is visible? Cool, cool. Then I'll start. Yeah, in this session, I just want to talk about how to build your own HackerFab. And the target audience for this is mostly students at colleges, although anyone else who's interested in chip fabrication can also derive value from it. So yeah, just putting it out there that the session is as like it doesn't assume that you know too much about the things we've discussed. So if you know a lot, then you might want to skip some of the more basic parts, but I'm assuming everyone knows some basics about the fabrication process. So yeah, I'll just begin now. So, yeah, before we get into the how, I just want to give you some motivation as to why we think you should do this and why I think we should be having a lot more hackerfabs in the country. So, firstly, what's in it for you? So, at least for me personally, semiconductor fabrication has always felt very magical. Like there's this very famous thing where people say you are literally teaching rocks how to think, and it's a field that has not been accessible to a lot of people historically, and normally you have to do a PhD at a top college to even get a chance to work with it. But now in today's day and age, we've progressed enough that it can actually be accessible to most people. So you will get a chance to work on something really cool which not a lot of people have got a chance to do. Secondly, it's an extremely interdisciplinary field. Like you have chemical, mechanical, electrical, vacuum systems, everything, and science as well. It's like the frontier of both science and engineering. So it'll develop you a lot as an engineer. Thirdly, you'll be able to build something of your own from scratch if you start your own hacker fab at your college. And that's something that's pretty cool. Like you learn a lot by doing that, even non-technically, and it looks very good, even if even from the point of view of your career. And yeah, in terms of your career, you would be in like less than 1% of electrical engineers who have actually built semiconductors with your hands. So I feel like it's quite fun to do, and everyone should be doing this. In terms of I'm just going to go through this very quickly, but I just wanted to give a bit of motivation. But how can this contribute to India's semiconductor mission? India's semiconductor mission needs tens of thousands of hands-on trained engineers. This is not a field which you can just study from a textbook and go to the fab that Tata is making and contribute over there. And today's day and age, we don't have the infrastructure to train all these people. So if all these people are not going to get hands-on training at the college level, how are they going to go to the fabs and immediately start working and deploy the 28 nanometer process? So we do need this happening right now to complement basically these top-down push of the government and the Indian semiconductor mission, where they're putting lakhs of crores. But if the talent doesn't rise to the opportunity, uh, we'll not be able to be successful. And I think the more ambitious goal for this is that there are maybe 5 to 7 colleges in the world today that like are able to do their own chip fabrication with tools built by students in such a hands-on way. And we see the potential that maybe we can have 50 to 100 of these in India itself. And if today we'll be producing the best engineers with the best talent, then who's to say 10, 20 years from now, why we can't be leading the industry, right? Because talent is one of the most important parts to this. So yeah, that's all for the motivation. I'll get into the technical stuff now. Before that, I've just given a list of all the references that we've referred to in our work, been heavily inspired by, and even for the presentation, the types of stuff these guys have done. So yeah, you'll learn a lot if you just go through the work done by these people. So I'll share the presentation after the webinar is done, so you can access these links from there. Cool. So, yeah, even though I'm assuming people know basics about fabrication, I'll just give a quick rundown on the fabrication flow. And this is a really good video. I like anytime someone asks me what they can do to get a quick intro. So if you don't know a lot, you can watch this video, right? So, yeah, there are multiple, like there are actually many thousand steps that go into a fabrication flow of a complex chip. But basically all your chips are made of transistors, and this on the bottom right is the structure of a transistor. So in the fabrication flow, and even in a lot of the work we do at HackerFab, the focus is how can we build a transistor, basically, because that is the building block for everything else. If you can figure how to build one transistor at a like within a small size, you can easily scale that up uh, a lot. So like a lot of the learning is at the level of building a transistor. So for the transistor, basically you start with a p-type wafer, and you want to make two n-type wells, which are your source and drain. And then you want a oxide layer, and above the oxide layer you have a metallic gate. So the applying a voltage on the gate basically controls the flow of current through the source and the drain. So, and you want all this to happen at a really small scale, basically. So the way you do that is, yeah, you grow an oxide layer on the wafer. You apply this photosensitive compound called photoresist, and then wherever you want the windows to be, you can just expose UV light through a mask to those windows, and that UV light changes the solubility of the photoresist, and it can be basically washed away in those parts. Then in the parts that the photoresist gets washed away, you can dip the wafer in something like hydrofluoric acid, or you can do a plasma etch, and you can etch the oxide away. So that will expose the bare silicon. And when the bare silicon gets exposed, you can dope that part. So that's how you dope these N-type windows. And then once you're done with doping the N-type windows and growing the oxide, you figure out a way to deposit the metal, and that's basically how you build your transistor. So very basically, we want to figure out how we can do all these processes in a simple way and a low cost way. So the goal is not to build something that will immediately have commercial value, but it's to build something that we can start learning from and we can get hands-on experience with. So yeah, that's the basic fabrication flow. If you have any questions related to this also, you can ask it in the Q&A. Jay is also well versed with this. He'll be able to answer that. Cool. So, what do you need to get started? And like now, there are a lot of misconceptions in this, a lot of things that people assume, which I want to say are not completely true. So, people think because it's semiconductor fabrication, you need a lot of money to get started. People think that it's not safe. People think that you'll immediately need access to chemicals. You'll need to deal with a lot of bureaucracy for your college to even get started. And only like for some reason, people believe that only certain types of people can do certain types of work, which is completely untrue. So anyone can do this, and it's as long as you want to do this and you're driven enough to do it, you can get started with basically nothing and start small and keep improving what you're doing. And I think any engineering college in India can do this. And yes, eventually you do need many of these things that we are talking about, but you don't need any of them to get started. And once you're able to get started and show progress to people, people will also help you to get the other things, right? So if you're able to show impressive progress, people do offer you money to continue making progress, or even if your college is impressed with what you're doing, they'll give you a space to work in. So yeah, you don't need any of this to get started. So then what do you actually need to get started? So I've not written it down on the slide, but I think one thing that you do need to get started is at least a group of 2 or 3 people who are passionate about this, because A, it's not fun, and B, it's not easy to do this stuff alone. If you have any complicated technical project, if you have a group of people passionate about it, it makes it a lot easier. So yeah, that's what I would say, that the first thing you should find is just a few friends who find this as interesting as you do. And yeah, that's all you need to get started, really. So yeah, how small can you actually start, right? Like how simple can it actually be? So I'm gonna start with very simple, and then improve, like improve the complexity of what you can do. So obviously when I'm talking about the very simple part, that stuff is not gonna seem as cool or as impressive, but I'm only doing it to demonstrate that you can start really simply. And when you actually build up to more complicated things, it does get quite cool and exciting. So yeah, most people, like, they don't even know where they can get a silicon wafer from, right? You need a silicon wafer to get started. So in fact, you can buy 4-inch, like you can buy a single 4-inch silicon wafer from multiple websites online. I have linked one website here. You don't need to do anything. It's just like you order anything else. You don't need to fill any forms, do any compliance. You can just buy the wafer. This one wafer can be cleaved into more than 30 pieces, and it costs around 2000 rupees. So a single experiment that you do with a single piece is no, like less than 100 rupees to do that. And in the beginning, the types of experiments you'll be doing, like applying photoresist and trying to do some lithography, you can like you can dip the wafer that's applied, you applied photoresist on, you can dip it in acetone, which is also very easily available, and you can clean it and reuse it. That will just strip away the photoresist. So you can basically buy a single wafer, and like your entire beginning stage can basically be done with just that one wafer. So yeah, it's not a lot. And in fact, if you don't want to go ahead and purchase a wafer to begin with, you just want to get started, you can even, like, for things like coating photoresist or even lithography, you can even get started with like glass slides, which are extremely inexpensive and easily available, the types that you use in microscopes. So yeah, you can start with glass slides, and eventually when you have some more money, you can buy a silicon wafer. So that's what you start with. You'll get some type of substrate, and then you cleave that substrate. If it's a silicon wafer, you cleave it into pieces. So because you don't want to waste such a big expensive wafer when you only need really small pieces to do your work anyway. So the fancy way is using a diamond scribe. A much cheaper and simpler way is you can just use two tweezers, hold them on opposite ends of the wafer. The wafer has a natural lattice structure. So if you just press with the sharp points of the tweezers, it'll break into two pieces, and you can keep doing that. You can find many YouTube videos which cover how you can do this. You should use gloves while you're working with these wafers, because your fingerprints will make them dirty. And you can store each of those small pieces in like small boxes or Ziploc bags, and if you want, you can clean the boxes. It's yeah, it's it's quite simple, right? So now you have your small pieces of silicon wafer. That's where you start from. Now what do you do, right? So uh, to do it, like the first process that you really want to start doing is you want to be able to coat films onto the wafer. So uh, like coating photoresist onto a silicon wafer is the first step you really need to do something like lithography, for example. So yeah, just a really quick rundown of how lithography works. You just coat a layer of photosensitive film onto the wafer, and then you expose parts of that film with UV light, and the parts that get exposed, they wash away in a developer, and you're left with the parts that you didn't expose, or vice versa if you're using a different type of resist. So it's very similar to how your old cameras in the olden times used to work. And yeah, so first tool you can build is basically a spin coater. And you can actually get thickness of these films of the order of microns with a very simple spin coater. So yeah, I would say this is a very simple tool you can build, and it will give you confidence. You'll actually be touching the silicon wafer, you'll be working with the chemicals, you'll be coating it, you'll see it work. It will give you confidence that you can also build this type of stuff. You can also work with the semiconductors. So the way a spin coater works is basically it's just you drop a viscous liquid of photoresist onto your wafer, and you just spin the spin coater at a really high speed, and that just pushes the liquid outward, and it makes an even coating. So yeah, and it's not a very complicated thing to make. And if you want to start really simple and have done this, you can literally use a CPU fan that is easily available on Amazon. You can take a small piece of tape, loop it around and stick it onto the fan, and then take your wafer and use the tweezers to push it into the tape. This will ensure that when you spin the spin coater, the wafer doesn't fly off. And then you just apply a voltage across the fan spins, and you get an even coating like this. So yeah, you can start really, really simple, and you have like at least a working tool with which you can do something. Then obviously, if this is something that interests you and you want a better spin coater, there are many simple projects that you can do. And this will all be parts that if you have any makerspace or tinkerer's lab in your college will be easily accessible to you. Like you can use drone motors, and these are all like parts made of acrylic and basic electronics, all sensors, stuff like that to check the RPM. So you can get RPM control, you can reduce the amount of vibration and stuff like that. So I have linked multiple builds over here. So if you're interested, you can make a better spin coater that can be, it can look professional, it can be your first device. You can coat wafers with it. You can demonstrate it to people, maybe your professors, college admin, someone who you're approaching to fund you. And you can say, hey, I've already made at least one basic tool that works, right? So yeah, I have linked some builds, and uh, these in some of these builds they use screws like this to hold the wafer down instead of tape. Obviously, tape is a very hacky way to do it, and the professional way to do it is you make a small vacuum chuck and you pull vacuum, and the vacuum suction basically holds the wafer in place. So this is a build which is with a vacuum chuck, and all these are I think all these builds will be like under 10,000 rupees to make. So yeah, if you want to make a professional looking device to show someone, this will be like the way to go right after that. But you can, even if you're not interested in this, you can move on and start doing lithography even with the films that you coated with the CPU fan, right? So yeah, I'm sure you're all wondering like where do I get photoresist from, right? So yeah, I'll admit it's not a chemical that you can just walk into a shop and purchase, but you'll have to figure out a way to eventually procure it. Like we get it through our college. You'll also probably be able to contact the chemistry department of your college. They'll be able to put you in touch with some vendors and you can buy it that way. And yeah, even though it's not extremely simple, if you just contact a bunch of people, you'll eventually be able to do it. And important thing to note is that if you are using photoresist, it's a bit expensive. So you should get a micro pipette to like dispense small doses of it. So you only need about like 50 to 100 microliters at a time. So if you're using 100 microliters at a time, you can coat like 100 samples with just 10 ml of photoresist. So yeah, but uh, if like this, I understand that it may take time to do all of this. You don't need to start with photoresist. So you can even do spin coating and lithography with like this 3D printer UV curable resin. This is easily available on Amazon. You can get like a really big bottle for 2,000 rupees. And I have actually linked some 20 micron features that I got using this 3D printer resin. So the resin, it's used for some part in the 3D printers, and the resin is photosensitive to UV basically. So you expose it to UV the same way you do photoresist, and it behaves quite similar to that. Obviously, like if you're at the stage where you're actually going to be building diodes, capacitors, transistors, you can't really use this at scale. But when you're just demonstrating your lithography system, developing your lithography system, this is like like it works like really well. And like so if you're spending maybe 2 months, 3 months building a lithography system, you can just go ahead with the UV resin, and in those 2 3 months figure out a way to procure the photoresist, right? So just because you don't have access to some chemical doesn't mean you need to stop there, right? There are options like this available, and I've not mentioned it here, but I know of people who've done like some basic lithography even using the films that they use for PCB making, which is also easily available. So yeah, you can find a lot of workarounds like this. So I would recommend you start with this UV resin. Cool. Then let's get to the cool stuff, right? Lithography. What is lithography exactly? So the basic point of lithography is that to etch any circuit or a transistor or anything, you actually need a physical pattern on your wafer. Now, that sounds quite complicated, and you actually need it at a very small scale. So, the first simplification is that we figure out that hey, UV light can react with certain chemicals. It reacts with those chemicals and changes its solubility, and the part that it reacted with can get washed away because it became soluble. So, you can basically transform the problem from making a physical pattern on the wafer to, okay, I just have to make a pattern with my UV light, and then wherever I make the pattern with the UV light, the UV light reacts with that part of the photoresist, and that's how I get a physical pattern. So yeah, so this is a much simpler problem to solve, right? Making patterns with light is much simpler than making actual physical patterns. So yeah, that simplification is already done by the chemistry of the photoresist. Now, one note on wavelength is if you're wanting to build things on a micrometer scale, the like wavelength of UV I would recommend is 405 nanometers. This is actually high enough that it actually overlaps with the blue spectrum. So you can actually even see this with the visible, like with the naked eye, because it's kind of also part of the visible spectrum. So it's not a very low wavelength. The lower the wavelength you go, it introduces more and more complexity in all parts of your system. Like the optics that you use, for example, have to be rated for that wavelength, and your camera has to be rated for that wavelength. So because for 405 nanometers is good enough at least up to 1 micron. So if you're not going to a lower feature size than that, this is the simplest wavelength to go for, and it's cheaply available also. Cool. So yeah, that's the first principles of how lithography works. And how do you start, right? So again, you should start simple. You don't need to make a full-fledged lithography system to just begin, right? So to just begin, you will first just be testing the chemistry of what you're doing, whether the UV light is actually reacting with the photoresist and doing what it's supposed to. So remember, I mentioned you can start with glass slides. This is an experiment I did on a glass slide. You can basically just apply photoresist on the slide, make a like mask with just paper, you can just use paper, cut out some holes in that paper, and block part of your substrate and expose the rest of it with a UV torch like this, which you can easily buy for like 1,000, 2,000 rupees from Amazon. So so the bottom right image, I just took like a tape or a paper and I just blocked half of the glass slide and I exposed the other half with this UV torch for some amount of time and then I developed it. So this is just to demonstrate that your lithography principle is working, and then you can make more and more complicated patterns with those wafers. You can mimic the structures of transistors and see that all that works. So yeah, all the point is that you can start simple and you can figure out the processes and then you can keep complicating it more and more. So the next step of complication is that you can basically make these masks that you can expose light through using these PCB stencils. So any PCB manufacturer like PCB Power, if you give them the design for some stencil, they will laser cut the stencil and like send it back to you. And these guys are typically capable of making features as small as like half an which is 500 microns. So you can make complicated designs like this, get the stencil fabricated from such a vendor. You can even simpler designs, you can even 3D print a part and expose through that. And you can get your basic lithography working and make your first patterns using this. And down like up to 500 microns features, this will work. And another important thing is that your feature size is not the only determining factor. If you get your entire process of how you do the spin coating, how you do the exposure, how do you develop, and you fine tune the parameters of all of that and get clean features, even if they're 500 microns, it's not that difficult to then use like some tricks and scale it down. Getting that in place is also a challenging thing and it will teach you a lot. So yeah, and I found this reference yesterday only. Someone used like this very similar method to actually 3D print some masks and make their own PCBs, like simple PCBs. And yeah, this is how they do it. They just expose the light through this mask. And yeah, you can, if you're interested in that, you can watch that, right? Even PCBs are fabricated only. So at this feature size, generally you have like PCB level fabrication. Anyway, that's how you can continue your lithography. And then if you want to, once you nail that, and all of that is stuff you can do really cheaply. So you can maybe everything that we've spoken about so far, you can maybe do in like 10,000 rupees. And once you have done all of that, you'll have like achieved many results that you can show people. You can show people the spin coater. You can show them nice intricate patterns that you made through the lithography system, and you can then kind of figure out a way to get some funding, maybe from your college or maybe from some donors. And I'll cover the funding part, how we went about it later on in the webinar. But my point is, once you have stuff that works and you show it, this is really cool stuff, people want to support you. And trust me, if you do all of this, you'll get some of the other support to continue it. So yeah, now if you want, like the actual cool part is you can going into like the 10 micron and below range, where you will actually have to build a proper lithography tool. And yeah, I'm sure you all are aware, but even like 10 micron is like extremely small. Your hair is like 70 to 100 microns, so it's one tenth the thickness of your human hair. So these patterns are not even visible through the naked eye. They're really small. You can only see them through the microscope, and like it's really cool stuff. So and there are a lot of references for such machines to learn from. I have linked all the good references that I have found. and the places where I learned it from. But I will also be talking about the basic workings of this system. So yeah, I would recommend you you can start building this lithography tool, or if you are tight on budget, there's a tool I'll talk about later, which is the tube furnace. You can build something like that for maybe 20, 30,000, and you can use that to oxidize wafers and then try to raise some funds for the lithography system. So yeah, but I do want to talk about how the system works, right? So again, like just from first principles, let's try to derive how you would try to build this system, right? So there are two ways that you can do lithography. One is the basic stuff which we did in the last few steps, which was using a physical mask to pass light through. And the other way is a different way. It's called maskless lithography, where you actually project a pattern directly with light. And so basically, if you want to get to below the 10 micron scale, to make a physical mask becomes really expensive. It's hard to find vendors who have the tools that are necessary to do that. And for every different design that you want to pattern, you'll have to make a separate mask. So you'll have to spend money again, you have to spend time again, and all of that. So that whereas with a maskless system, where you just directly project a pattern, you can make any number of designs and you can make it extremely cheaply. So for our purposes, where we want to make something cheap that we can do 5 micron, 10 micron lithography with, the maskless idea wins, right? So, okay, we know we want to make a maskless lithography system. How do we make a maskless system? So what are the requirements? The requirements are that it should be able to send any arbitrary pattern, whatever pattern you want, it should be able to send it. And uh, yeah, basically, that's all we need from a maskless system. It should be able to use light to send any arbitrary pattern. And I mean, do we know any easily available product in the market that can do that? And the answer to that is yes. It's a projector, right? A projector is something that you connect your HDMI cable to, and whatever pattern that is, whatever your laptop screen shows, the lights inside the projector project that same pattern outward. So it's exactly what we need. And that is exactly how the beginning of these maskless lithography systems, these DIY versions, this is exactly the thought process that they started with, that, hey, I just need to make a pattern with light. A projector does exactly that. It makes a pattern with light, which you send from your laptop, and it projects it out. So why don't I use a projector and do something? So there's some technical detail that most of these systems use a specific type of projector, which is called a digital micromirror device, or a DMD projector. It's also called DLP, which stands for digital light processing. I'm just telling you so you know the words for it. So like it's good when you're using something, it's good to know how it works. So it's just like we like this diagram over here is just explaining how the projector works, right? Internally. So internally inside the projector, so I'm sure all of you have used projector sometime or the other. So you have a resolution, right, for the thing that you're projecting. So your full HD resolution is typically 1920 cross 1080. And all that is just the individually addressable pixels to which you can give a RGB value, and all those pixels together make your entire image. So technically, you just need each pixel to be individually addressable to some RGB value. So the way that these DMD projectors achieve that is that each pixel, they have a chip which is made by Texas Instruments that's inside the projector, and each pixel has on that chip a corresponding micro scale mirror that is corresponding to it, and that mirror can be controlled by a very tiny motor, and that motor can basically turn the mirror into an on or an off position. So in the on position, which you can see in this diagram, the right side is the on position. It projects into the projection, it reflects into the projection lens, the mirror. And in the off position, it just reflects into some light absorber. So at any given time, you only see the pixels corresponding to the mirrors that are in the on position. And because you can turn them on or off for red, green, and blue individually. You have a cycle where your projector first sends red, then it sends green, then it sends blue, and you can individually turn them on for how much ever time you want. So, say you want the combination color of red and green, you'll turn that pixel on for the red cycle, on for the green cycle, and off for the blue cycle. And the cycles basically happen so fast that you basically when you look at it, it appears as one color for you. So yeah, I'm just explaining how this projector works. So uh, when you actually send a HDMI pattern through the HDMI cable of this projector, you're actually individually addressing each of these pixels. And yeah, so that the size of the pixel determines how small of a feature you can get with this projector. So, yeah, so that's basically the internal working of this projector. And because these mirrors themselves are quite small, the projector does a lot of the work for you to be able to actually make these small features. Cool. So, now, the obvious question, right? You use a projector to make things big, but we want to make things small. So how does that work, right? And that's a very simple problem. So the projector has optics at the exit point which project things outward. We just remove these optics, like we just literally unscrew the optics and replace them with demagnifying optics. And these demagnifying optics are, you know how you have a microscope? Your microscope makes things big. If you use the same objective of the microscope in reverse, like you project light from up rather than looking at a sample bottom, that same objective will make things small. So right here, you can see this is a photo I took from Sam Zalouf's YouTube channel. He just put a projector, removed the optics from the entry of the projector, and just projected it on from the top of the microscope. And then at the place where you normally keep your sample, the light demagnifies over there. So yeah, this is a very simple demonstration of how that works. So uh, so yeah, so normally this is the inside of your projector. You have optics that are screwed in here that are actually projecting outwards. And by the way, if you see that that small rainbow colored chip in the center, that is your DMD chip. Uh, One sec. Yeah, I think I can maybe start annotating. So yeah, so this is your DMD chip, and these are where your optics are basically screwed on. So you can literally just unscrew these optics, and then the next step is one sec. Yeah, the next step is you use a microscope objective like this in reverse, and you can demagnify with that. So you just remove the optics that magnify and replace with optics that demagnify. And these are like the standard objectives that you use in any lab microscope that you can work with. Cool. Uh, Next, don't we need UV? A projector works on visible light, right? We need a UV source. It's again a very simple workaround. You just remove the light source of the projector and you replace it with a PCB which has UV LEDs on it. So this is a schematic of the PCB we use, and you just solder some easily available UV LEDs onto this schematic, and yeah, you just screw that UV LED in, where initially the projector we had a red, green, and blue LED. So we just unscrewed the blue LED out and screwed a UV LED in, which we just these PCBs are basically copper core, and we found that the Indian vendors were not able to do copper core PCBs very easily. So we got it done from JLC PCB, which is a Chinese vendor. But the PCB can also be made fairly easily, and the schematic is already available. The LEDs are also quite cheap. So you can just make your own UV source like this. Like I said, 405 nanometers. And yeah, you just replace the light source like that. So is that all? Like you replace the light source, you demagnify, that should be all, right? Like you demagnify, you get a small image. So it's not quite everything because the image is really small and we still don't have a way that we can actually focus this image. And because the demagnified image is so small, we are not able to determine whether the focus is done with a naked eye. Remember, like your microscope will demagnify the image and it's like a convex lens. It's going to focus it only at a single point. So you need to find that point accurately. And for that, you need to be able to see the image. So we need some way to inspect. So we just add a slight complication in our optics, which is we stick a beam splitter into the path from the projector to the microscope lens, and we divert some of the light away to a camera. And now that camera can basically be used to inspect. So the way this works is you have your projector has light that okay, first let me just explain what a beam splitter is for people who don't know. A beam splitter is very simple. So imagine you have light that comes from here and you the light hits the beam splitter, right? What the beam splitter does is that in some ratio it makes the light reflect, and in some ratio it makes the light transmit. So it does both things. So how that would happen is that the light will come from the projector, some of it will go towards the microscope lens, and some of it gets reflected into this junk direction, right? We don't really care about that light. But what actually happens is what the interesting part actually happens after it hits the silicon wafer here. Because the silicon wafer is reflective, the light will reflect back. It'll again get magnified while it passes through this lens. It'll hit the beam splitter here. Some of the light will go here, which doesn't really matter to us. But some of the light, because it's a beam splitter, it'll get reflected here and go into our camera. And because it's gotten remagnified and then goes into the camera is able to see a big image. And when it's able to see that big image, we can now inspect whatever is going on in the wafer, and we can move the wafer closer or farther away until we get a focus. So yeah, this is basically how the optics work. And you just have to match the distance from the projector to the beam splitter and from the camera sensor to the beam splitter. So the DMD chip to the beam splitter and the camera sensor to the beam splitter. As long as those distances are matched, you will get the image converging at the right point. So this is the only basic complication we have in the optics. Uh, cool. Next, how do we actually focus, right? Do you remember I said we have to bring the wafer closer or farther away? And this actually has to be done quite accurately. Although you can try a bit doing it with hand and it works a little bit. The more sustainable way to do it is you have a micrometer scale XYZ stage. So these screws can be turned and they move the stage forward, backward, and actually in all three axes, because you can then move the wafer around in its plane as well. And the screws basically move the stage in like micrometer scale steps. So you can turn the screw and the stage along with the wafer, which can be held by a simple vacuum chuck, will move forward and backward, and you just move it closer and closer to the microscope objective, uh, which was uh, here. You just move it closer and closer until you get a sharp image, and that's when you know you're focused. So yeah, that's basically all all that is there, right? You just have some of these mechanical parts that we got fabricated locally, and that's hold the stuff in place. So like inside this cube, you have the beam splitter. Your objective is screwed in here. This is your camera. Your camera is screwed in here. And this is a like a development kit of the projector that we bought. But you can just buy a projector also off the shelf. And this the optics used to be here. We just replaced that and screwed our own mechanical parts in. So yeah, that's all the parts that there is. Here, this is the projector. There's a beam splitter over here. There's a microscope objective over here. Camera over here. This is our stage. We have screwed in a 3D printed chuck to the stage, and the stage just moves forward or back. And in the bottom here, we replace the light source with the UV LED. That's all, like, that's basically how simple it is. And later on, you can connect stepper motors and control the stage automatically and all. But all that is small additions you can do later on. So this is basically all you have to do to make the lithography system. And yeah, obviously, if you have questions, you can continue asking uh, Jay in the Q&A, and I'll also be happy to answer later on. But yeah, that's all there is. So uh, yeah, I'll move to the uh, procurement part, right? How do you actually buy all the components that you need from this? Let's start with the projector. So we actually because the designs we were following used the development board which is sold by Texas Instruments, and this is the name of the technical name of the board. We went ahead and directly bought this, and it cost us 1.5 lakhs landed. But that's basically because we wanted to like for like replicate a design, but we did not actually have to spend this much. So the development board is actually something that Texas Instruments sells to projector manufacturers because they buy the Texas Instrument chip to make their projectors. But anyone can go on their website or you can go to Mouser and buy this. So this costs 1.5 lakhs. That's what we work with. But actually, you can buy off the shelf new DMD or DLP projectors for like 50 to 60,000, and these are available in India. Like one brand I found is BenQ, which sells these DMD projectors. Just make sure to go into the product brochure or data sheet of the projector that you're buying and ensure that it has a DMD chip inside it. You'll be able to find that. And in fact, if you're not able to find a product brochure or anything, you should just check your model number of your projector. Just check it online. There are many projector review communities on the internet. You can just search reviews of these projectors and you'll find these communities. And you can just search for the technical name of the projector, and they will, on the community, you'll find posts where you'll get to know the product brochure and all of that. And you can in fact buy these projectors used as well. So I found some vendors on Facebook Marketplace that are selling these used projectors. And in fact, some of the some of the earlier iterations we did, we used one of these. And even projector repair shops, if they're anywhere near your area, they'll have these. And you can get these for like 10 to 20,000. And lastly, there is something that our team is exploring, which is that this projector that we bought from Texas Instruments was a big, more complicated projector, which is for like the ones that are sold for maybe classrooms and lecture halls. But if you ever seen those smaller projectors like of Zebronics and all, they have like a much smaller chip inside. So we found some smaller dev boards that are sold by Texas Instruments where the exposure size is not a lot, but the resolution is still the same. So by resolution, I mean the mirror to mirror distance, which is what determines your resolution. So these we were able to find for like 10 to 20,000, and I'll show you what we've been doing with this a few slides later. So maybe if you're not able to comfortable with or not able to find these projectors easily, you can go ahead and purchase these. So because we were doing it for the first time, we kind of went with the safe option and bought this dev board. But now, if anyone's repeating it, you can buy a lot of this cheaper stuff. That's for the projector. Then for the optics, right? Yeah, you basically need two main optics, which is the objective and the beam splitter. And I would say in both of these, don't rely on cheap ones because your optics can make or break whether your system works or not. So get a good quality objective, and I've linked the exact objective and beam splitter we bought from Advent Optics. You just have to make a purchase order on their website. They send you an email and you can buy it. They have an office in Delhi. It gets imported from China, but they do all the work for you. It gets delivered directly to your doorstep. So this costs around 20,000 and this costs around 6,000. Cool. Uh, for the camera, right? So I'll tell you the most important thing for the camera is that you should have a lens that is either removable or you buy the bare camera without the lens. The reason for this is that the image is already getting magnified from the objective before it goes into the camera. So you want your camera to see the image as is. You don't want the lens to do something to that image after that. So yeah, that's when you're looking for cameras, that's the main point you have to keep in mind. Uh, we wanted to go for a big sensor size so that we can view the entire exposure field. So the with cameras, the bigger the sensor sizes you go with, the more expensive they get. So our camera costed like 80,000. But yeah, like we basically lot of the procurement we did, we tried to go on the safer side and get over spec things because we wanted it to work. But now I can confidently say that a much cheaper option for like 5,000, 7,000, which has a smaller sensor size, will also work because you need your camera sensor to only see a part of the image because at least in the beginning, you're only using your camera to do the focusing. So you can, if you're doing this project again, you can get much cheaper options with the camera as well. Uh, yeah, that's the camera. And then the other stuff, right? The XYZ stage, you can search for a micrometer XYZ stage online. You'll get many vendors. We ended up buying it from some Chinese vendor for like 8,000 rupees. And yeah, the other mechanical parts to hold everything into place, we actually we spent like maybe 30,000 on that because we had some more complicated design. But based on the principles that I discussed, you can actually redesign the system quite simply and use very basic, maybe even 3D printed parts, and you can really cut down on this cost as well. So it cost us maybe 3 lakhs to make this, but if you do it smartly now, it's possible you'll be able to make this system for even under a lakh. Yeah. So that's the procurement. And this is what I was telling you about. We are trying to basically work on this low cost system. So I just took apart the optics from our current setup, and these are the small TI dev boards I was talking about. So these are really small projector boards. And instead of using that big 1.5 lakh projectors, these cost between 10 to 20,000. I'll be happy to share the technical name for this later on. And yeah, so this is the same optics and same stage, and this is like a checkerboard pattern that we captured using, we projected using this projector. And we are basically trying to simplify all these mechanical parts and all and bring the cost of this system down to under a lakh. So that's something we are still doing. But based on all the principles we discussed, you can build onto this concept and easily make something that costs under a lakh. Cool. That's all with the lithography. So yeah, if you have any questions, I'm just gonna come back to the meet and see that everything's fine. Uh, cool. If there's any issue so far, just drop something in the chat. No, cool, no issues so far. So assume assuming that, I'll just continue. Uh, let's go to the next part, right? The next part is oxidation. So you basically silicon and silicon dioxide form a really good interface. So any type of thing that you're doing, like I spoke earlier about the windows that you etch to do the doping, the easiest thing to do is you just grow an oxide, and the oxide acts like a physical mask on the wafer through which you can make those windows, and it protects the rest of the wafer. And even for your NMOS transistor, your gate will have a gate oxide. So even that gate oxide, although more complicated in the industry, they work with these dielectrics, specific dielectrics that they deposit. You can even use silicon dioxide as your gate oxide. So for that, what you do is you can either consider building or purchasing a tube furnace. So tube furnace is a really simple like device which just heats up, and it can go up to 1100 degrees, and you can control its temperature. And we built one, actually two freshers from our team built one, and it costs around 30,000. So that's why I was mentioning that if the lithography system is something that is really expensive for you, you can consider building one of these for 30,000. You'll even be able to oxidize some wafers. The oxidized wafers actually have really beautiful colors. So it looks really cool. So you can show people that you build a device, you oxidize wafers through it, and you can even use that to kind of build more credibility. So yeah, this is something you can consider building. I'll very simply explain the way it works. The way it works is that like most, like I'm assuming everyone knows that when you pass current through the conductor, through any conductor, the conductor like the like resistor, basically due to the resistance, you lose that energy through heat, right? So you're just using the same principle and passing a lot of current through a particular type of material called canthal. And canthal can basically, it's a conductor that can handle high temperature. And yeah, I'll just move to the next slide and continue the explanation. So yeah, by the way, the silicon oxide is something that just grows because of the oxygen and air. You don't even need to pass any gas in. Anyway, I'll get back to the explanation. So this is how we built the furnace. This is Rushat and Abhineet. They're freshers in our team. They just finished their first year in college. They built it by themselves. So this this winding is like you take this canthal wire material, you wind it first on a lathe machine. You can wind it into a spring because that becomes like the optimized way to do the heating. And then first thing you do is you make a mold, right? So you take two PVC pipes. On the inner pipe, you wind this canthal. You put it on the inner pipe. You fill this like this special type of cement that can refractory cement, it's called. It can handle high temperatures as opposed to normal cement. So you fill that cement in this mold, and then you pass current and heat it up to cure the cement. And then once the cement gets cured, you can basically just remove the PVC pipes. You can remove the inner and outer PVC pipe, and you're left with a mold like this. And so the mold basically acts as a insulator for the heat that's gonna come. If you don't make that, then the heat will escape very easily. But this cement can really insulate that heat, and it also basically it sets onto the canthal wire. So now your wire will also not move anywhere. And after that, all you do is you just place a quartz tube inside this mold, and the quartz tube is where you actually do your experiment. So when you pass current through this canthal uh, filament, the quartz tube inside heats up. You put your wafers inside the tube, and yeah, that's all. And then you can basically use a thermocouple to actually uh, measure the temperature inside, connect that to your electronics, buy a basic PID control module, have a target temperature, your thermocouple will, which is inside, will have a known temperature, measured temperature, and your PID control loop can basically go to your target temperature. And all of this is very basic electronics. You can put it in a box, connect it to your mains, and just connect it to this Kanthal winding. So that's all. And we were able to get really good plus minus 2-3 degree control over our 1100 degree range for this. So yeah, that's how the furnace works. And one more thing I want to mention is that most of the parts for the furnace, like there are a lot of people who build furnaces in India for labs and all. So most of the parts of the furnace are easily available with local vendors. You just have to talk to some people and find out where those vendors are. And you can come on our Discord, and maybe even Abhinit and Rushat can help you with the names of the vendors they got this stuff from. So yeah, using that you can oxidize silicon wafers. Cool. Uh, Next part, right? This next part is etching. So once you grow an oxide layer and then you do lithography and make these windows through the photoresist in the layer, you actually have to remove the oxide under those windows to be able to reach the silicon, to be able to say put dopant over there if you want to dope, or if you want to metallize that part, you deposit metal. But you actually need to remove the oxide. Now, unfortunately, the only chemical that can react with silicon dioxide is hydrofluoric acid. And hydrofluoric acid is an extremely toxic chemical. So, it's extremely toxic in the sense that if even a little bit of it will come onto your skin, that fluoride ions can basically seep into your bloodstream. And like in small doses also, it can cause, like it can stop your heart from functioning. So you need to be extremely careful when you're working with these chemicals. The fumes are also toxic. It's toxic to your eyes and it's toxic to your skin. So you basically need, firstly, you need a wet bench, which is just a wet area to work with chemicals, which has a tap. It has all the basics that you need to work with chemicals. You need a fume hood, which is like a chimney which will suck the fumes that your hydrofluoric acid will generate, because those fumes are toxic. And you need to wear the full PP and you need to work with extreme care. And for this, you will need permission from wherever you're working. You should preferably get properly trained on the proper operating practices to deal with these chemicals. So, like all colleges will have like some chemistry department or whatever, they will have their safety protocols in place and they deal with chemicals that are even way more toxic than hydrofluoric acid. So they can teach you how to get the right protocols. But this is something I would say that don't take it lightly at all. You just want to do it, so you're doing it, because it's like there are a lot of accidents that happen in this, and it can be extremely dangerous. That said, like labs every day on a day-to-day basis do use this chemical, and they don't meet with any accidents because they follow the standard operating procedures and safety protocols properly. So if you do that, if you understand what that is, take the right permissions and do that, you can do this safely. And you don't have to get scared of doing it, but you need to know that there's a proper way to do it. And because there are so many people, I mean, it's my responsibility to tell you to, if you're doing anything like this, be very careful and take permission from the right people. So, yeah, but unfortunately, there isn't a safer way to do it unless you build like something called a plasma etcher, which is a complicated system to build. And this is a much simpler way to do things. So, it's better to get follow the right protocols, get the right permissions, and do this, then build a really complicated tool. Because this is where, like, once you set up the right protocol, this is extremely cheap and easy to do. So yeah, that's how you do it. It's the hydrofluoric acid basically just reacts with silicon dioxide and washes it away. Cool. That is the etching. And the next part is doping, right? So if you have a P-type silicon wafer, like we saw in the transistor, and you want to make N-type windows in that, how do you introduce that dopant? So the industry does something called ion implantation, which is an extremely expensive tool to make, very complicated. It's not something that any hobbyist level pay anyone has yet built. And we found many people have done this much simpler doping method, which is called spin-on doping. So these standard recipes are there, which are sold by companies where they sell you this chemical which has the dopant. Like say you want N-type phosphorus doping, it has the dopant inside the chemical itself. So you can just buy the chemical from them. You drop the chemical onto the wafer and you spin coat it using the spin coater, and that will make a like layer of that dopant. And in fact it's made of it's made of silicon dioxide only, so it basically forms like a layer of glass on your substrate, but that glass is doped with phosphorus. And then what you can do is you can basically put that into the tube furnace, which, assuming by this point you already have a tube furnace, the heat of the tube furnace basically causes the phosphorus from that glass to leach in, and that leaches in and dopes your silicon. So yeah, that's how you do doping, and it's a much cheaper way to do it. We bought the chemical from this company called Filmtronics, based in the US. There are not a lot of companies that make this. It cost us around 1 lakh, but that chemical will last us maybe many months or a year even. But the only issue with this is obviously it's very expensive for a chemical, and at the customs you do need to handle some paperwork because it's corrosive. So you'll need to figure out a way to handle that when you're importing it. But there is something that I would recommend because it has been done by many people. It is they make a DIY recipe for this dopant. So you can use easily available chemicals which are available very cheaply and locally, and you can make your own recipe for this chemical, and it costs only a few thousand rupees. So I've linked a YouTube video where someone has made a DIY recipe for this. So if this is out of your budget, you can always go and make something like this. From what I've seen with people who've done this, this can maybe achieve like 80-90% as good as this. So it's definitely worth doing. Now the step after that is metallization, right? So if you have a device, you eventually need to probe your device, pass current through it, measure voltage. You can't do any of this without making contacts. And even your gate that controls the channel inside your MOSFET has to be made of some metal that can create an electric field, right? So for your gate deposition and to make contacts, you need a way to metallize. And this is something we built just this year. And it's by far the hardest and most expensive tool to build. So you should have done all the stuff we've spoken about before you do this, because you'll need to raise some more amount of money, and you will need to put a lot of effort into doing this. But unfortunately, you have to do it that way because there's not really a very simple way to do this. You need to make a proper tool to do this. So uh, that being said, it is still very much doable. There are a lot of people. We also did it in our lab. It will just require a talk of its own to get into the nitty-gritties of what what goes behind actually designing and building something like that. It'll cost between 4 to 7 lakh depending on multiple factors. There are two possible tools you can build for this. One is a thermal evaporator. The thermal evaporator literally just evaporates the like it. You have a metal the same way you pass current through the tube furnace. you pass current through a tungsten filament. In this case, your metal is kept on the tungsten filament. The filament heats up. It melts the metal first, and then it evaporates the metal. And once the metal is evaporated, you do all of this in a high vacuum, and creating that high vacuum is what adds to a lot of the cost and complexity. But you basically do that in the vacuum. So when the vapors of the metal move in vacuum, there's nothing obstructing their path. So you can basically just keep your substrate up and the vapors can just go and deposit onto it. And that's the easier tool to make. The more like very much cooler and more versatile thing that we ended up building first was a sputter, but it'll cost also a bit more. But anyway, sputter is basically you use high voltage plasma in like argon environment at a certain like low pressure, and the high voltage makes plasma of the argon, and the plasma attacks a particular metal, and that metal falls onto your substrate. So yeah, if you're wanting to eventually make say a 10 micron transistor, you do eventually have to do something like this. But if you're making really big devices, so you can even take like this big of a wafer and just make one transistor in it, just for the sake of learning the whole process and making the transistor. In that case, you'll have really big terminals. In that case, you can use this silver-based conductive epoxy, which is much much cheaper, and you can just buy it and make your contacts with that epoxy. So it's a very hacky thing, but if you're making big devices, this is I just thought I'll mention it's something you can do. Cool. uh, Last part is making devices, right? Even after you make all the tools, you have to make working devices with it. You want to make capacitors, you want to make diodes, you want to make transistors, you want to get the textbook curves. And believe me, when you start making it, your curves are not going to look anything like how they look in a textbook, because that is when you'll understand the complexity, challenges, and difficulty of semiconductors. And when you will actually debug that, that is when your real process engineering learning will come. That how do I make like this isn't working? How do I make it work? Should I change this step? Should I change that step? Should I make my oxide thicker? Should I sputter for longer? Things like that. And it's like I can't say anything about this other than it's really fun, and you will only learn it by doing it. And it's a really unique opportunity to be able to do this. So if you're and like if you're fascinated by semiconductors, really making like your first capacitor or your first transistor will be like a really fun process, and it'll definitely be worth it. Cool. So yeah, the theme of the flow of all of this was basically start small, iterate, and become more and more complex. That's the best way to do things. Don't get overwhelmed by trying to build everything all at once. Start simple and keep making progress. And that's how we did it. We started August last year. It's June right now, and we made our first capacitors and diodes, and in the process of making our first transistor, we built all of these tools. And believe me, there's nothing much that special about us as engineers. We just figured out that this thing we are passionate about, and we did it. So yeah, I think that's the technical part of the presentation. I'll get into some advice maybe for funding and logistics. Again, I want to reiterate, as I demonstrated before, a lot of what you need to get started doesn't cost much and can literally be even done in a hostel room or a small tinkerer's lab in your college for maybe under 10,000 rupees. Even if you're 15, like say if you have three friends and you decide to put 5,000 rupees each, you can start doing this stuff. So your spin coating, your lithography with the UV resin, and the hand drawn mask or the stencil mask. And believe me, you show some nice patterns to people in your university or your college or some donors. And these days semiconductors are really hot word also. They'll realize that people in their college are building semiconductors. I'm sure someone or the other will help you out. in terms of the funding. And these days, colleges have technical teams for all types of things, right? If you have a racing team, you have a robotics team, you have a satellite team. If they can get funded, why shouldn't this also get funded, right? And to begin with, you just need 1 or 2 lakhs to build the basic lithography system. That's, I think, if once you get some funding, that's the first thing you should start with, and you get the micron scale patterns with this. And I guarantee you, when you show someone that there's a pattern that you can't even see, and it's such a complicated pattern, and we built this all in our literally we built it in a hostel room and some small lab space, and like this will impress a lot of people, and that's how people got impressed by us and funded us. And eventually, maybe to build out all of this, you'll need a total of around 15 lakhs, which may sound more or it may sound less, I don't know, depending on who you are. But uh, this is around the same budget that a lot of college teams operate at. So you're working, even though you're working on something extremely expensive, you're still working the same amount of money as some drone team, racing team, electronics team. So why shouldn't you be able to get this type of funding, right? So yeah, so just talk to professors, talk to your admin, find one person who's willing to support you, who'll help you out and do all of this. And eventually you do have to get some cooperation with them. You might have to make some proposals, get them to sign off on it. We are always there to help you. We've done the same thing. We can help you do all of that. And you'll need a small lab space, which is at least having a wet bench and a fume hood. And you'll need permissions from your colleges, but that is all eventually. My advice to you is just get started. There are a lot of people who have a lot of ideas, but they don't get started. If you get started and start building things, people will favor you over all these people, and you will get the funding and support that you need. Uh, some more points. One thing that I've realized not a lot of people know is that there are many micro grant programs that you can apply to. It's like a 15-minute form that you can fill online. I've listed two of them, which in fact gave us some funding. And they are they are basically they give you the money, no strings attached. Some of them are philanthropies, some of them are venture capital firms who are just kind of looking to support some people. And you just have to impress them with the work that you are doing and whatever vision that you have, and they give you money. So both these, initially we also did not apply for funding through our college because we didn't have anything to show to them. And now so we applied to this grant programs. They gave us a few lakh rupees to begin with, and that's what we needed. And like I've just listed two. You can just Google micro grants and micro grant programs, and you will get a list of maybe 10 or 15 such programs, and you can apply to them. And if you show us some progress that you're making by working frugally, we have gotten a lot of people who told us that they want to support the cause, right? Or they want to fund us. Now we have already gotten the support we need from our college, so we can connect maybe you to those people, and you can maybe pitch to them that, hey, IITB started this, we want to start something similar, here's the progress that we've made, why don't you fund us? So I'll be happy to make those connections for the people who have got in touch with me with the interest of funding this. So yeah, basically, just please don't consider this stuff to be a constraint. It will all get figured out one step at a time. And believe me, if you put in the effort to build something good, you will get the funding and the support you need. Lastly, how can we help from our side? These are all the ways that we can help. Just join our Discord. We have channels for every single topic. You have lithography, etching, tube furnace, sputter, and we've gone through all the resources that we need. So if you're stuck on something, we'll maybe send you a YouTube video of someone who solved that problem. Or if we solved that problem before, we'll tell you how to do it. We'll brainstorm with you. This is stuff that we are also very passionate about. If there's something we know someone from CMU has done, we'll direct you to the global Discord. I have linked that as well. You should join it. And the global Discord documentation is also very good. You should go through that. And if there are still issues that we aren't able to find the solution to, like I told you, we'll also be as curious as you are. We'll consult our professors and we'll basically get to the bottom of it. So yeah, we are not a startup. We are not looking to make money out of this. We just want more colleges to do this, and we are passionate about this, and we want to help in whatever way we can to make that happen. Yeah. So uh, that brings me to the end of the presentation, and yeah, happy to answer any more questions that exist. Cool. Yeah, I think you can raise your hand. So I'm seeing two hands raised. I'll just allow you to unmute and ask the question. So I think Deepak Prajapati, I have allowed you to unmute. You had a hand raised. Cool. One sec. Allow my. I'm allowing the people who have raised their hands to unmute. So if you've raised your hand, try unmuting. Let me know if there's an issue.
Hello.
Hello. Yeah.
Yeah. Myself Madhusudan.
Hmm.
Yeah, you told you had done capacitor and few diodes.
Yeah.
So I didn't understand why we need there is no transistor, right? For capacitor, the fab is required.
For capacitor, what is required?
There is no transistor, right? So the process, whatever the semiconductor etching, all the
Madhusudan,
process.
a MOSFET's heart is a MOSFET. So it's not like a regular capacitor, which is two metal plates the dielectric. It's a metal,
Okay.
dielectric, and semiconductor. And the reason we build a MOSFET is it's the first step to building a MOSFET. So if you have a working MOSFET, then you need to add the source and drain.
So MOSFET is just the whole stack of the capacitor without the source and the drain. In that, when you add the source and the drain, it becomes a MOSFET. So it's not a ordinary parallel plate capacitor or something that we have made. We made a MOS capacitor.
Where it is useful? Is there an application?
So it is used, for example, in RAM. Like you have MOS caps in RAM, but the main reason we are building it is because it's the first step to building a MOSFET.
Okay.
And a lot of the art of how your MOSFET works is in how you engineer the capacitor that is there. So if you get the like correct CV characteristics of your MOS capacitor, then your MOSFET will work properly. So a lot of the debugging of how your MOSFET works is in the way the capacitor is designed.
Okay. So you also told diode, you have implemented diode, right?
Yeah.
Diode. So how good is means can it get into market? Is it capable?
No. We are not building anything right now that can get into market. This is basically the diode we built was just to demonstrate whether our doping method worked or not. And if our doping works, then the once we can make the MOS capacitor and then do the doping, we'll be able to make the transistor. It's like a very complicated process to make something that's good enough to get to market. So that's still a very like it's still very far away before that happens.
Okay, nice. And I'm basically a working professional. So so for any startups, I understand it's for college point of view. I understand it will be helpful for students and upcoming engineers. So how you connect it to industry? So this kind of fab. Is so how you in so connect
So
between these two?
So right now, we personally are doing this mainly for education and training, but we have some ideas of making low cost tools. Like for example, one idea is that low cost tools can be made to make like digital twins of tools, and there is interest from the industry for that because that's like a new thing that people are pursuing. So if you have low cost tools, you can put a lot of sensors into those tools and model the tools basically. So that's one thing. There are multiple things like that, but right now our focus is mainly on the educational aspect and the training.
Okay. And you mentioned some of the fund, right? So they
Yeah.
want some little amount of proof that you have done something, or they can help you at the very initial stage itself.
So we got basic funding at the initial stage itself. They just evaluate you fill a application form and they do an interview and they evaluate you, and if they think that you'll do something good with it, they give you some initial funding even if you've not done. But if you do some basic work before that, then it creates a lot more credibility for you, but they don't expect you to already have done a like lot of great things before you get funded.
Thank you,
You're
Aryan.
welcome. I have unmuted a few more people. You can ask.
Hello,
Hello. Yeah.
am I audible?
Yeah, you're audible.
I was asking Lois, like I just came into the second year, so how
Yeah.
should I start? First, I'll build a spin coater. That is just a CPU fan. After that, should I move to litho, right?
Yeah, so you can do like the basic lithography which I spoke about using the UV curable resin and the torch. You can start making small patterns with that and demonstrating it, and you can also probably make a nicer spin coater. The CPU fan is good, but if you make a nicer spin coater that looks like a good product and it has low vibration, you can control the RPM. That will be a good thing to show someone because like spin coater is a tool that's used all over the industry as well. So making a DIY version of that, even though it's basic, it's a good start. So I would say do the basic mask lithography and make a nicer spin coater after that, and then take it from there.
So, like on YouTube, there are two videos. One of Masi spin coater and other is Bird, I think something like that.
Hmm.
Which do you think is the one that one should go with? Like the Masi one, kind of I felt it is easier, whereas
Hmm.
the Bird one was complicated. They are using Raspberry Pico and it was a bit complicated.
So the electronics and all is so you can do it however you want to do it. It's just one sensor that senses the RPM and then just a control loop. That electronics that is up to you. It's much simpler than any other electronics project you would have seen. In terms of how you do it, I don't think it really matters. If you want to make something really impressive, I have linked one in the PPT. I've linked one build where someone used a vacuum chuck. So I have not seen a lot of DIY builds with a vacuum chuck. So if you can make that, that would be the most impressive. Otherwise, just make whatever you feel like making. Just make that. I don't think there's a much big difference between all these different builds.
So
You can
should I
also
buy
just
a silicon wafer or go with the reflective glass coating for reflective coat for
you can
initial day?
for building the spin coater, you can just use normal small glass slides. You get like I think like few centimeter by few centimeter square glass slides. Just buy a pack of those. You can start off with that, even lithography. And then later on, if you want, you can buy the silicon wafer. It's not a compulsion to buy immediately.
So I start with the litho and the spin coater I'll build alongside. It would be
Yeah, so maybe
right
in the
away.
beginning, what you can do is make the CPU fan, get the CPU fan, the glass slides, and build the basic UV resin, build the basic spin coater with that. Start with the litho side by side, and side by side make a better spin coater. and maybe that's the best way to start, I guess.
So I guess it would take around 3 to 4 months to build a litho, right? A proper functioning litho.
Yeah, proper functioning litho honestly may or may not take that much time, right? Once you have a design, the main thing is just that you have to order all the components and they have to arrive, and then you have to assemble it. Assembling it is very easy, but then you might have some small issues that you will have to debug, or sometimes it's easy to get the pattern in the camera, but you have to try a bit harder to get it on the wafer, because you can overexpose the wafer, you can underexpose the wafer, things like that. So that will take trial and error. But yeah, the full proper functioning litho, 3 to 4 months is a good goal for that.
And in the video, like the runtime BRT video, you were telling about the projector that you guys are using was you guys were going for a very small one. You were talking about it.
Yeah.
What was it? I was confused about it.
So you saw the full big litho. There was this big projector, right? In that.
Yeah.
So one sec, I'll just share my screen. Is my screen visible?
Yeah.
Cool. So if you see here, no, one sec. I have to annotate. Yeah, do you see where my marker is right now?
Yes. Yes.
This is a really small projector. It's a projector only. Where the light is coming from, it's projecting through that. So this is the engine that's inside your small tabletop projectors that you get. So I'll like, you can join the Discord. I'll tell you the exact name of this projector. So it's just two boards with just like kind of like a shield, and they both together cost like 15,000 rupees. So it's much cheaper than going for the full size one. It's just that the exposure size is smaller, so your total image becomes smaller. But you do, anyways, if you're making a transistor or something on that, you're only going to use a part of the screen. You're not going to use the whole screen. So this is good enough to get started with.
And you know, on Amazon there are 5,000 and 4,000 rupees projector that's 720p. Is it good?
Yeah, yeah,
Like
yeah.
someone can use it?
So you can try, but the thing is that all the builds that I have seen specifically use a DLP projector. So DLP or DMD, they are both names for the same thing. So it's a specific type of projector which I explained about those mirrors. So that is something that I have not seen people succeed with a different type of projector. So that's not to say it cannot be done. I've just not seen someone do it till now. So I would say safer bet is, if you have, maybe go for some 10-15,000, then this, or you buy a second hand DLP projector.
Yeah, it was. I was just giving a suggestion that it would be great if you start a voice channel or Discord, so like many students can come there and chat about their projects, or maybe you guys, when are free, you can also join and guide us. It was
Yeah,
just a
sure.
suggestion.
We'll be happy to do that.
Yeah. Okay. Thank you very much.
Welcome, welcome. Uh, one sec.
Hello.
Hi.
Hi. Yeah. I'm Akash. Basically, I saw all your presentation. Like, it's actually very good. Thank you for that. So, my question is like, do you have any bill of material, something like that? Like, I'm completely not from fab, like basically chips and all. I do robotics and all. So I
Hmm.
don't know much about this. So, is there any bill of material so that I can look into that and hack it out, something like that?
Yeah, sure. So, what we'll do is, by tonight we'll post the bill of materials of all our tools on the Discord, different channels for the tool. So Discord, if you're not on the Discord server yet, join the Discord server. We have channels for every tool. We'll post the BOM for those tools over there.
Yeah, that would be awesome. And also, like as you mentioned in the previous conversation, like you are interested in building digital twins, something like that, right? Like,
Hmm.
so like I'm also planning like since in robotics too we have to build actuators, right? Currently the
Hmm.
actuators cost is hell lot, like something like 60% of the robot cost is actuators. So I
Hmm.
thought of building an digital twin version of that, and later get it fabricated CNC and all. So
Hmm.
I just want to know what's the area that you are interested in, like in the digital twins.
So we have not really explored it yet, but we were told by our professors that what they want us to build is like make like a model for the machines that we are making. So we have a vacuum chamber based putter. Now they want
Mhm.
us to model all the dynamics inside that so that we can make a digital twin for it. So companies can use that to design their processes. So it's very early stage. We've not really looked into it that much, but it's something we are open to look at in the future. But yeah, not a focus area of focus right now. But yeah, we can discuss more about that on the Discord maybe.
Yeah, sure. And also, like for the design of the chips, what tool or something that you're using? Like I saw like Flux and all. And what do you think about this AI design tools, like for chip design or all?
So our chips are extremely basic in that
Mm-hmm.
if you look at a mask cap, you're just having rectangles as the mask. So we literally made it in GIMP or Photoshop, or you can just make it with holes in aluminum foil. What you
Yep.
learn in VLSI design or chip design is designing actual like large scale chips, right? The V in VLSI is for very large scale, like a CPU or something. So that requires a proper software to organize all those transistors. And there, of course, there's a lot of scope for AI to improve, like doing automatic routing, just like you have for PCB. So
Mm-hmm.
yeah, but yeah, but we don't use those.
Yeah. Yeah. Thank you. Those are the questions. Yep.
Sure. Yeah, I've allowed people to unmute. Anyone can unmute and talk. Who's had their hand raised?
Hi, Arman. First of
Hi.
all, cool stuff and great work with the HackerFab.
Thank you.
Uh, I had a question around so right now the full ecosystem that you shared about the projectors and the etching process and everything, it feels a bit scattered. So do you plan on standardizing this and maybe building kits out of it so that people can buy it out and then set up the lab in their homes as well?
Yeah, that is something that we want to work towards. In fact, what we actually want to work towards is for people who don't want to get into designing the tools, we want to basically make a like fab in a box type of solution. So we just put all these tools into one kind of container, and the parts that need to be clean will be inside the container. The rest of the stuff will be outside the container, and you even use the small AHUs and all to clean keep the inside like a clean room. And because it'll be a small size, it'll be cheap or to even maintain a clean room like environment. Otherwise, you can do this stuff without a clean room also. Like we don't have a clean room in our lab, but it'll be better with a clean room. So we want to automate and integrate all of it, but it's probably at least a 1 year project to do all of that because it's like it's not very difficult, but it is time consuming.
So, like, do you have any contribution guidelines or something like some guide or something like that so that people can actually contribute towards this or to
We
build
don't have a
something like
guide,
this?
but we are always posting our live progress and questions on Discord. Like we always have questions to do with hardware, software, everything. So you can literally start by just answering those. Just browse the channels every day, like see Litho V1, see Sputter. But in future, as we our scale grows, yeah, we might have official guidelines. But it's very informal right now. Just go ahead and answer.
Even like it doesn't have to be like so right now things are very unofficial and informal. It doesn't have to be our idea also. Even if you have some idea, you can just suggest it to us that why don't you guys try to do this. We'll try to tell you as much as we know about the tools and what we've built. And then once you have the idea, anyone on the server can suggest things and we can explore those options. But yeah, unfortunately, one thing we've not done well is we've not documented things well. That's also why I did this, because if we had documented things well, we could have just shared the documentation. But yeah, our team will work towards that now. Then if we have better documentation, all these things will become much easier.
Yeah, sure. Thank you so much. I think that would be a great way to start with, the
Yeah.
contribution and everything.
Yeah, so we'll
Thank
work
you.
on that now.
Yeah.
What are the things that HackerFab at CMU achieved, like compared to IITB?
So at CMU, the things that they have achieved that we have not is firstly, their sputtering system is slightly more advanced than us. They have a RF sputter, we have a DC sputter. So the DC sputter can only coat metals, whereas the RF sputter can coat dielectrics as well. So tools wise, that's the only thing that they have which we don't. But process wise, they have actually fabricated 5 micron transistors, and they've done it with good yield. So we are still in the process of getting our transistor fabrication process right. So they started, in fact, they started 2.5 years before we started. So they had that head start, and they built on the work of this guy, Sam Zaloof. So Sam Zaloof was doing it for years in his high school. So obviously we kind of had their work as reference, so we could do it much faster. But those technically it is those two things. They're fabricating transistors with good yield, and we are in the process of doing that. And the sputtering chamber is slightly more advanced. Other than that, one more thing is that they have integrated the HackerFab into the coursework at CMU, which we are planning to do it next semester at IITB. So, yeah, so people who take like VLSI technology courses can in IITB can come work in the HackerFab as well as part of their coursework. So, yeah, that's basically the differences right now.
Do they guys help you like when you get stuck?
Yeah, they do help. I mean, in especially in the sputter, I spoke to their team lead quite a bit. Like we are in good touch with them as such.
Like, can you guys arrange, if possible, you can arrange some session that in which CMU, some lead or maybe one member can join, like this webinar type?
So they
I,
have a public Discord just like us, and you can ask questions on there directly, which you want. So it's very open and free. If you specifically want a meeting for some reason, then maybe you can DM us. But unlikely to be needed unless you have some technical doubt, which is hard to explain on
Okay.
chat.
Can you just share the link of their HackerFab Discord at
yeah,
our
it's on
Discord?
I've put it on the PPT. So once I share the PPT afterwards, you can just find it there. Cool. More questions? Yeah, I think I've allowed everyone who has raised their hand to use the mic.
Hello.
Yeah.
So I was asking, in the litho process, you said that,
Hmm.
we were giving it a kind of what we call it. Well, I'm a high schooler. Sorry about it. We were giving it the image, we can say, to the, so it
Hmm.
projects it to the silicon essentially. So how exactly we like connect HDMI and connected to the software and just projected it? Like,
Hmm.
what was the software, or how
So,
we designed it?
the simplest way you can do it is you make whatever image you want, you create a PowerPoint slideshow, you put it onto the PowerPoint slideshow, you connect your projector to your through HDMI cable to your laptop, and you just present in the slideshow mode. It will come out through the projector. That's all you need to do.
Like, just design in PowerPoint whatever we want to
Yeah, you can design in Paint, you can design in GIMP, you can design in Photoshop, whatever. Take that image, put it into PowerPoint, connect the HDMI cable, and present. That's all.
Oh,
Just like how
nice.
you watch, how you have slideshows. Now, if your professor is doing some lecture, he connects the projector to the HDMI cable and he shows the presentation. No, what they do in corporate offices also same thing. Same way. You just put your pattern into the PPT.
Got it. Thanks.
Hello.
Hi.
Actually, the process you are explaining to make projector, is that the same way display is created? Or
I actually am not aware. We'll have to Google it and see. I don't know how displays are made. Maybe if Jay knows, then he can comment.
okay.
Cool. I think we'll have to look into that. I'm not sure about that.
Hello.
Yeah.
Thanks for doing what you people have done. It's quite great to see. I just wanted to know, like, whatsoever you people have built right now in litho and in doping, like, what more we can just improve just to reach to like real fabrication stuff, just like say to be market ready or to just do a bit more improvement. And like a bit more like what these company are like doing different in litho, like just like ASML, they're doing advanced
So
stuff. So like what we can work more on to. Thank you.
The thing is that our litho currently is at a micrometer scale, which is 1,000 nanometers. The ASML litho works at nanometer scale. So in terms of resolution, they are like 1,000 times where these basic DIY versions can get you. And when you want to go lower and lower in resolution, every part of your system becomes more and more complicated. So you need to use a lower wavelength of light. Because of that, you need different optics. To make the lower wavelength of light, so what ASML is able to do is that they have a light source that is able to make 13 nanometer light with very good intensity, which nobody else in the world is able to do. Whereas, and their optics are made by a company called Carl Zeiss, and Carl Zeiss is the only company that's able to make optics that are able to handle that light, and they don't just absorb it. So there is no comparison or like pathway to how you get there. This is mainly just to demystify the concept of lithography, that the concept of lithography itself is not that complicated, and we can learn a lot about it by doing this. I don't really see us continuing this work and maybe doing exactly what they do. But the point is that if people get exposure to semiconductors from a early age and they get the hands-on experience they need, maybe the 20 years from now, 30 years from now, the bottleneck that the industry will face then could be solved by someone who is today doing something like this. Not necessarily the goal is to displace the current players. It's just to get the hands-on experience you need to create an impact in the industry in the future.
Okay, I'm just like just it's not related to this, but I think if like ultimately like to do something like in real world fabrication, what this
Hmm.
company or like TSMC these people are doing. So like what you people think like could be done, huh? Like it's required a lot of energy, sorry, money and energy, to be spent by a lot of people in India, like literally in our country. So like what we could done at like industrial scale, like we are
So
just doing it for learn ourselves. Okay, thank you.
yeah, if you mean the country as a whole, as you would know from because of the India Semiconductor Mission, India is having fabs come up, and they are like advanced fabs, 28 nanometer, which Tata is doing, and those will produce chips for us made in India. But if you mean you yourself, you want to make chips in the industry, then you have to like join the industry as an engineer. And there's if you're asking about how a venture like us can grow into catering to customers, then you can look at something at Inch called Inch Fab in the US. So they also have a similar concept of a fab in a box, which they sell to customers. But the economics there are very different, and that's not what you're catering to right now because it's very hardcore and it's very tough to get profit and sustain.
Okay, thank you. But we still should try, I think.
Sure, we'll see where it goes. We'll see how far we can go.
Yeah, Raman. I have one question about procurement. How did you manage the procurement of those vacuum components and chambers? Uh, I mean, the local vendors, it was all.
You're not audible.
You're mute. I
Hi, sorry, I was on mute. So, the vacuum pump, the primary pump, which is like the rotary vane pump, you can get locally from vendors like Hind Vac. And like they can make chambers and all also. What we did is, in fact, we fabricated our own chamber. We just bought a stainless steel pipe, like pipe piece from a steel vendor, and we just polished the inside, and then we just welded some flanges to it and CNC'd a top and bottom plate and screwed it in, and used some O-rings for sealing. And the for the high vacuum, the pumps you need, mainly you need a turbomolecular pump. So we bought a second-hand turbomolecular pump from eBay. So you can get second-hand turbos from eBay for like 1 to 2 lakhs landed. So that is how we did, because if you go to buy these pumps new, they're very expensive, but they are built to last for many, many years. So a lot of these labs, they have surplus, so they list it on eBay as second hand and you get it much cheaper. And we luckily found someone who was delivering to India, but for some components, we did not find vendors who were delivering to India. So we used this the like shipping forwarding service from the US, which just takes the delivery for you and forwards it for a small fee. So I'm just writing the name of that service in the chat. So any vacuum part, if you're not able to find it in India, just go on eBay, search for it, deliver it to that shipping forwarding service, and they'll deliver it for you to India. And second-hand parts are like you will get 1/5 or 1/10 of the cost of the original ones, and they work just as well because it's like very reliable engineering.
got it. I also want to know that your DLP based the lithography, markless lithography. What were the hurdles in the patterning of 10 UM resolution compared to that traditional
The
process?
hurdle is actually mainly a process hurdle. It's not a system hurdle. So, getting your development time, exposure time, all of that right, and consistently getting the pattern, your wafers are clean, your all of that was a bigger hurdle in terms of getting the final resolution than the projector system itself. For the projector system itself, I would say the only possible challenge is that you have to do the distance matching between the DMD chip and the beam splitter and the camera sensor and the beam splitter. So if that sometimes it's a bit like complicated to do that, but yeah, if you want to simplify that, and a very simple thing you can do is you can buy a second XYZ stage and put your camera onto that. Then you will get really accurate adjustment of that distance matching also.
And the specific fabrication process, do you use also some software, like EDA software also for the integration for anything
We
like that?
don't we don't use right now we don't use any software. Actually, there's a nano fab at IIT Bombay. So they have standard recipes for certain things. So we just try to follow the similar recipes as they are doing. And the professors and all suggest what to do because it's not very complicated. We don't need any software to keep track of it.
Yeah, okay, thank you.
Yeah.
And also the documentation is important, I think.
Yeah,
If
yeah, I
this,
agree.
yeah.
Hey, I just wanted to ask, like, so, uh, when, like, while you are getting the parts and all, so generally, like most Indian suppliers and all, like they do promise to send you the level of quality we require, but they often don't. And also, like, uh, um I tried Chinese supplies a few times, but they since the level of since the batch is very less, they kind of send it kind of broken products or something like that. So how did you guys manage it? I just want to know that.
So we did not have, luckily till now, we've not had any such experiences. But I would say if you're facing issues like that, the expensive parts that you get, buy them from brand names only. Like if you're doubtful about that, just buy a projector from, if you're buying a projector, buy it from the official website of the brand or whatever. And yeah, I mean, even like you can find for anything, you can find what the reputed brands are and then just buy from them directly.
Yeah. Okay. Thank you.
Hello.
Hello.
So my question was that can we also make some kind of like basic digital circuits from this process, like a NOT gate or NAND gate?
Yeah, once you're able once you're able to make transistors, then you can make basic circuits like that. You can make gates. People have made like six transistor amplifiers also, and you can maybe even make a current mirror, things like that. Very basic circuits you can make. Anything that maybe involves maybe less than say 10 transistors and doesn't need multiple layers, you can make.
Okay, thank you.
More than that, you would need a lot more sophistication in the way you do things.
Okay.
Cool. All right.
Hey
Does
Aryan,
anyone? Yeah.
yeah, great presentation so far. So during your presentation, you had said that the devices that you will fabricate in the end won't actually follow textbook curves. So how do you go on to debug that? Because the process being so vast, you actually can't pinpoint where the process went a bit right or left.
Hmm.
Yeah.
Hmm.
Yeah,
So,
you're absolutely right. So that's the job of a process engineer, and it's a very valuable skill to develop. So in general, we first try and make sure the individual tools work according to certain specs. So with our litho, if we can say we can repeatedly get 5 micron features, then we know that it's unlikely to be an issue when we make the canvas. Now, if it's because the curves are mismatched, like the mask cap still works, but the curve is a bit wonky, yeah, those are harder to debug. But it mostly just comes down to removing contamination. Like that's the biggest. Like if we just were in a magical vacuum or a good clean room, most of those issues would go away.
Okay, makes sense. Thank you.
And also your DC plasmas, which you have built on a quartz crystal monitor. So how accurate that is of how accurate the deposition rate compared to the industrial grade sensors?
so we have not yet finished building the quartz crystal monitor. So we don't have like in situ estimation of the thickness, but we have gotten we've characterized the curve later on, and we have gotten around 10% roughness at a thickness of around like 300 nanometers, roughly. So I'm like we have not looked into how good that is as per industrial standards, because for us the main purpose of the tool is to make the contacts and the gate, for which if you have like 10% accuracy, like 10% roughness, that's good enough. But yeah, we can look into it.
Okay.
Yeah, I see 4 more hands raised. You guys can go ahead. Uh, anyone? Go ahead.
Yeah. Good evening, everyone. Uh, I would like to ask you a very not so technical question, that how did exactly you guys went into this? Like, how exactly it was decided this, yes, we want to build a lithography machine or a hacker fab or things like that? Like, how
Yeah,
exactly?
sure. Sure. So actually, I have two seniors, Abhineet and Karthik. Three of us together started this around August last year. So the main motivation was two of them had taken a lot of semiconductor courses, worked a little bit in the nano fab and all, and realized that यार students को इतना ज़्यादा chance वगैरह नहीं मिलता, you're not getting the exposure we need, so we should do something about it. And then Abhineet came across this work being done at CMU. So the two of them approached me because they knew I was interested in semiconductors too. And we saw that multiple people have done this. So we are like, if other colleges are doing it, why can't we also do it? So then we just started doing it, and we did some basic proof of concepts in 1 month, and we presented at a conference at IITB, whatever work we had done. And from there, we got like really positive response from industry folks, professors, all of that. So then we realized कि कुछ तो अच्छा है इसमें. So then after that, we really put a lot of effort into it.
Okay, thank you so much.
You're welcome. Are there any more questions? Cool. If there aren't, I'll end the call right now. I'll share the slides and the recording as soon as possible on Discord. Thank you all for joining. Really overwhelmed by the number of people that attended. And I hope at least some people from here go ahead and make their own hacker fabs. All the best.
Thank you. Thank you very much.
Thank you for doing this. It was great.